Okay, so I'm here today to talk to you guys about how to decarbonize buildings in New York City. So I'm going to first talk to you just to give a brief overview of the New York City energy landscape, just to figure out, put into context some of the local laws that have been put into play. I'm going to talk to you guys about how to approach projects that can address some of these local laws and use your existing systems to future-proof your designs. I'm going to go through a couple different ways that we can go down the decarbonization pathway, and then I'm going to end with a case study of a local co-op building that my company worked on. So I know many of you are aware of some of the local laws that have been put into place over the past couple of years, but I wanted to just recap and just put them into context. But before I do that, I want to pull up this graph because I think this one really puts everything into perspective. This chart is from the Mayor's Office of Sustainability. It does an inventory of energy usage in New York City. And as you can see, 2/3 of energy usage in New York City comes from buildings. And specifically, almost 1/3 of it comes from residential buildings specifically, where there's a lot of usage per each apartment. And so this really, if you think about it, is a big driver into why some of these local laws were passed in recent years. The first big one was Local Law 33 and 95, basically issuing energy grades to buildings over 25,000 square feet. It basically just measured energy efficiency and energy usage per square foot that and plotted it based on all of the buildings that qualified and gave them a letter grade and an energy score on a scale of 0 to 100. Then Local Law 92 and 94, which really affect new construction and major renovations of buildings that are putting forward to have to either incorporate a green roof or solar panels on top of the roof. Unfortunately, in New York City, this isn't going to have as much of an impact on your energy usage just because in New York City, buildings are so tall compared to the amount of energy usage. So a green roof or solar panels on a rooftop are not going to provide a ton of green energy, but it's a start. And then the final one is Local Law 97, which is progressively setting limits of carbon emissions per square foot for these buildings. And this is where I'll talk about it later in the context of the case study, but this is where our goals of reaching a sustainable future are coming into play, where we're going to try to progressively lower our carbon emissions in our buildings. Now, a lot of these regulations or a lot of these things that have been passed in the past couple of years are not only targeted at regulating building owners. We have Local Law 96, which established PACE financing, which is a way to create low interest financing options if you want to tackle a larger capital project that's targeted at Local Law 97. And so this is a way that building owners can really capitalize on low interest financing programs to help them create a project. The cool thing about this is that it's tied to the actual building, not the building owner. So if you are working on a project and then you sell it halfway through, or you sell it, while you're still paying off the loan, it transfers over to the new owner. But the next two, the New York State Clean Heat Incentive is a really cool incentive program that was introduced that is really putting pressure and making it really viable to switch over to electrification. In New York City, it offers $200 per MMBTU, which is 10 times what the existing incentives are for switching from natural gas to electrification. And so this is really a way that it's making these electrification projects more economically viable. And also to note that this doesn't replace the other incentives. This can be done on top of it. There were a couple of projects we were working on where we were doing our normal incentive, and then we realized that we could also apply for this, and it really helped increase the economics of the project. And then the last one is the Climate Leadership and Community Protection Act. Yes. And that is basically putting the same pressure that Local Law 97 puts on building owners on the state and the utility companies. It's putting metrics into place to progressively make our grid greener. over time. And I'll get into this a little bit later in more detail as well. But just to go back to Local Law 97, there's a couple nuances that we can really think about as we move forward. The first one is that Local Law 97 is going to put limits in place, but if your building is performing significantly better, it's actually going to reward you by at some point installing a carbon trading program, where if you're significantly below the cap of that year, you can actually sell your remaining cap space to another building that may not be reaching its goals to create a new revenue stream for your building. That's not yet defined yet, but it's coming. And so it's something really to keep in mind when you're designing projects, not to just get just under the limit, to think about getting as low as you possibly can. With that said, electrical emissions is important to note, because every type of energy in New York City has a carbon emissions factor related to it, whether it's steam, gas, electricity, oil. And the way that New York City is moving forward towards electrification, the electrical emissions factor has to evolve in order for us to reach the Local Law 97 goals of 2050. If this electrical emissions factor doesn't improve, electrification projects alone won't get us to our goals. And then the last thing is that there's just a slight difference between Local Law 95 and 97, where Local Law 95 looks at energy usage in your building, while Local Law 97 looks at carbon emissions in your building. So it's actually possible to design a project that fully addresses your Local Law 97 goals while not having a huge impact on your Local Law 95 grade. So while Local Law 95 and all the letter grades that you see are kind of daunting, you look around and see Ds and buildings in the 20s and teens, it doesn't mean that Local Law 97 is unattainable, because you can completely address your carbon emissions and your fines, which is actually what's putting a lot of pressure on building owners, without affecting that score too much. So as we look at Local Law 97, I plotted the carbon emissions caps over time for the residential occupancy group, high-rise residential occupancy group. And the way that I look at it is it really puts Local Law 97 into two phases. We have our first phase, which is already defined. We have 2024 and 2030, which 2024 sets the initial emissions cap. So 2024 sets our initial emissions cap, and then 2030 is where we're going to see about a 40% decrease in carbon emissions in that limit. So this is really the bulk, the biggest step that Local Law 97 is going to have on the buildings. And then after that, they haven't yet defined how the caps are going to decrease down to 2050. 2050 is defined, but getting there is still in the gray area. And so the way that I see it is that we have the first phase, which is going to be more on the building owners to address their on-site energy usage and to look at ways that they can be more efficient and electrify as much as possible. But then, because of the CLCPA, the grid is going to have to get greener at the same time. And so as we get into 2035 and 40 and 45, those limits are going to change as the grid gets greener and the grid removes those carbon emissions factors. So I like to call it a team effort because we're going to have to work, or I say we, building owners are going to have to work with the utility companies in conjunction to do their part in lowering building emissions. It's a site versus source battle, but I don't really see it as a battle. We're really on the same page trying to lower carbon emissions to as a whole. But with respect to how building owners approach it, they sometimes see Local Law 97 as impossible to reach because of where the grid currently is. But I implore all of you to think of it more as what can building owners do to address thermal energy usage, because we have to remember that the utility companies are going to have to make the grid greener on their own, and there's nothing that a building owner can do to change that factor. And great news, this just was announced yesterday. 2 new power lines were just approved by New York State to make that first step in making our grid a little bit cleaner. One's coming from upstate New York and the other one's coming from Quebec. And this is really amazing news, because you think about it, how is New York City, which is completely provided electricity by Con Ed's combined cycle gas power plants throughout the city. There's some renewables on the grid, but you think about how in the world are we going to get down to a 100% zero emissions grid? This is the first step. So that was just a little primer on the energy landscape. Now I'm going to get into some ways that we can design projects to help us move towards this goal. First, we have to understand what we're dealing with. And this is another chart from the Mayor's Office of Sustainability. It plots buildings and how far away they are from Local Law 97. Blue is the 2024 limit, orange is the 2030 limit. And it makes a lot of sense that more buildings are not going to be compliant with 2030 than 2024, but you can see all the way on the right that there's over 6,000 buildings that are over 100% away from the 2030 limit. That means that they're going to have to cut their emissions in half. And also this puts into the caveat that there's buildings that are 200% away, 300% away. So those very, it's all kind of grouped into one, but there are buildings that are going to have to undergo a large change. But there's also a lot of buildings that are close, and those are the ones that we are going to be looking at in the case study. So looking at the buildings that we have and how we can shift it towards 2050, I looked at 4 different cases. One is if we took a building today and we just plopped it in 2050, we made no changes to it, the grid hasn't changed at all, and we looked at all of the buildings that are going to be affected by Local Law 97 in the residential category. And I found that over 90% of the buildings are going to be fined, and the average fine is going to be close to $100,000. Now, if we do our part, if building owners do our part, and we electrify, let's say 80% of the building, I'm not even going to go to fully electrified because I'm going to talk about that a little bit later, but let's say we only do 80% electrified heating, it really doesn't do as much as we thought it would do alone. It drops it down to 80% and it almost halves the fine. And then if you look at the flip side, let's say the grid gets cleaner, but we don't do anything to get ourselves onto the grid, it has almost the same effect. 80% of buildings are fined and we have about a $56,000 fine. But then you put those two things together. If the grid is clean and we do our part in getting onto that grid, the number of buildings that drops down is 5%, and with the average fine of $400. And if you think about it, all of the buildings that are going to be fined are the ones in that far right category that were 200, 300% away from Local Law 97 to begin with. So it's really attainable when we put it into the perspective of what building owners can do. The other thing that we need to think about is how do we use systems that are already existing in our buildings and look at how they can be leveraged in the future. So I took a couple different heating systems and plotted them in there. The x-axis is their emissions impact, and up and down is your life cycle costing. And you can see most buildings right now are either Con Ed steam or on a steam boiler using natural gas. And you can see on the right side, as we get lower in our emissions, we start to move towards electric heat pumps. The circle in the top right, a hybrid air source heat pump, is a concept that's going to be explained in the case study, but I just want to throw this out there that looking forward to our goals and looking at how we design projects, going with one option sometimes isn't the right answer. And so I'm going to explain how hybrid air source heat pumps fits into this category. But just going back to how to address the long-term goals now and future-proof our projects and future-proof our buildings, we need to think about not just 2024. We need to think about 2030 and 2050, because if your building is undergoing a large enough capital mechanical asset renewal project, you can't just look to see, oh, how do I get under 2024? Because by the time you build that project, you're going to have to go back out and bid another project that is going to have to get you under 2030, and then another one in 2050. And so most buildings fall under case 1 or case 2, where you're either already under 2024 limits or very close to it. And so the way that I see it is that we really need to think about how to design these projects to get us under 2050, with the caveat that even though right now we might not address local law 97's 2050 goals, but if we assume that the grid is going to do their job, we can already design projects that are going to get us under these limits. So now to focus more on building decarbonization, I see two main ways that buildings typically approach decarbonization. One is a centralized path, and the other one is a distributed path. A centralized decarbonization electrification is like if you wanted to install a air source heat pump array on your roof and connect it to your existing hydronic network. It does have a lot of benefits to going with a centralized path, where you do have some redundancy in your system. You can put an extra one up there in case it goes down, and so your system stays online. It's a little bit quieter since it's not actually in the spaces, but it does have some cons. The first being you actually have to have a hydronic network to capitalize on a centralized system. You do have to still do a seasonal switchover if you're injecting at a central location, because you're either operating your heat pump in a heating or cooling mode. That's only if it's a 2-pipe system. If it's a 4-pipe system, you're good, but not too many buildings have 4-pipe systems. And then the other thing that you have to consider is that a lot of buildings in New York City are a little older, and so they might not have the electrical capacity to handle a large centralized heat pump installation. On the other hand, you have a distributed heat pump system, where it's like a VRF system or a package terminal heat pump, where each space gets its own little heat pump. And the advantages of that are that you can you eliminate your seasonal switchover. So you eliminate your seasonal switchover because each space can operate its equipment as is, but the issue is that you remove that redundancy in your system. If that goes down, that apartment has no heating or cooling until you replace it. And then the other con is that each apartment then has to have the electrical capacity to handle that increased load. And so these are the two main systems. And so just looking at sizing heat pumps, what we did is we looked at a heat pump application where we sized it to handle the full building's load at 40 degrees Fahrenheit. Let's see. Very cool. So I plotted the building heating load in blue and the air source heat pump output in yellow. And as you can see, right around 40 degrees, we are fully covering the building's load. But one thing to note is that as the temperature gets colder, two things are going to happen. One, you have less hours in the day that are actually at those temperatures. A majority of your temperatures are going to be in that mid-range temperature bin. And then two, your air source heat pump is actually going to derate itself. The capacity is going to decrease because it's harder to pull heat out of the cold air. And so when you look, so this is charted by capacity, MMBTU per hour. But then if you look at the actual building's energy usage in these temperature bin counts, you see something really interesting, where if you have that same heat pump sweet spot sized for 40 degrees Fahrenheit, you're actually able to cover a majority of your building's energy usage from that heat pump. Even though it's derating, you're still able to cover it. But what you have to do is you have to combine your heat pump with another system to make up for that derating. And so what I looked at is we looked at sizing it in conjunction with a condensing boiler system. And so as our heat pump derates, our condensing boiler kicks on to cover up the remaining heating load. And then what we did is we looked at putting this just into a pie chart. And this is really compelling because even though we only sized our heat pump down to 40 degrees Fahrenheit, we're able to cover 82% of our building's energy usage from that heat pump. And then our condensing boiler is only running 18% of the year. So now to put it in action, I'll go through this case study that we worked on. We have a really beautiful co-op building in Union Square. It's about 156,000 square feet with 172 units with some commercial space in the basement. They already had a 2-pipe hydronic system that was connected to a gas-fired absorption chiller in the basement that could be run in heating mode in the winter to bypass the absorption part. But it was a big headache on the maintenance staff. They had to continuously, every twice a year, they had to switch over their system. Each apartment had a fan coil already. They could control its fresh air and control their temperature, but only within whatever mode they were in. And then they had a cooling tower, a massive cooling tower on the roof that didn't have much redundancy. Whenever it went down for maintenance, they had some problems. And so their chillers and the cooling tower were approaching the end of their useful life, which I'll get into a little bit later, but that was one of the things that we were really drawn to in this project. And then if you look at their energy costs and their energy profile, they were spending about $375,000 a year. And that's a combination of what the tenants paid through sub-metering plus what the building paid for with the central systems. Local Law 95 was giving them a D, about a 20, which is even lower than the average building. And Local Law 97 was going to give them a $100,000 fine in 2030. So this is just simple one line of the system, just to put it into perspective how everything connects. We have our chiller heaters in the basement tied to the fan coils on one side and the cooling tower on the other side. So when we approached this client, we were initially brought to the fact that their chillers and their cooling tower needed to be replaced. And so that became their primary project driver. But this client was very ambitious and they were aware of the changing energy landscape. And so they were looking to tack on some additional project goals. They wanted to reduce their operational complexity of having to manually change over their system twice a year because it's a big headache with the old system. And furthermore, they had some tenant recommendations that they really wanted to be able to control their spaces individually and not be tied to whatever mode the building was in. And then while talking with the client, Local Law 97 became a lot clearer. And so one of the project drivers immediately became eliminating their Local Law 97 fines. So with these 4 things combined, we started looking at several different scenarios, and we started with a like-for-like equipment replacement, and we really quickly ruled this out because there's no way that a like-for-like equipment replacement is going to address Local Law 97. So we really shifted our attention to converting the building into a water source heat pump with new terminal units, new boilers, and replacing their cooling tower. So we were doing the asset renewal, but changing the system a little bit. And then we also looked at what it would take for a full electrification project. And this is a brief summary of what those 2 viable solutions posed. If you look at just the status quo, they were looking at a $100,000 fine. They were well above the 2050 limit. And if we go to the full electric scenario that we looked into, we see that we're fully addressing their thermal greenhouse gas emissions. We're putting them fully electric, and also just want to caveat that this is assuming that the grid does their job. I'm assuming that by now in 2050, the CLCPA has taken care of everything and the grid's green. So they have no Local Law 97 fines because they're not emitting any greenhouse gas emissions, even through the electric grid. But their operating expenses do increase because it's fully electric, and based on the rates that we're looking at now, electricity is more expensive than gas per energy. And then we looked at the second scenario also, and we saw something interesting. We saw that we weren't completely eliminating their fossil fuel usage, but we were still getting under the 2050 limit, and we were decreasing their operating expenses. To go back to that full electrification project, as we were designing it, we started running into some design challenges that were really putting a damper on fully electrifying the building. First and foremost is that full electrification requires a large additional electrical capacity in your building that most buildings can't handle without a feeder upgrade. And so, a Con Ed project would have had to been explored where we have to bring in a whole new electric service. Additionally, as your heat pump derates, and on that previous slide, it'll show up again, but as your heat pump derates, if you want to fully cover your electric load, even at your 15-degree design day, you have to install so much more capacity. It actually, in this scenario, it came out to we would have needed 3 times the capacity of air source heat pumps to fully cover the electric load. And so there was a capital impact where the capital cost tripled just for the equipment cost, and then additionally that the physical space required for these heat pumps tripled, which was no longer viable with the given roof that we were dealing with. And so all of those two things combined, plus the fact that when you're fully electric, a new issue comes into play where you have no resiliency if the grid goes down. We get another Hurricane Sandy or any natural disaster where the grid goes down, we're out of luck. And so those things combined made a full electrification project very difficult to, in good faith, recommend. So when we were looking at a hybrid electrification project, we realized that not only was it avoiding some of these pitfalls, but it was actually bringing additional advantages. So just to recap, I think I've talked about all of these things already, but the hybrid electrification project that we settled on was sizing our heat pump for 40 degrees Fahrenheit, which reduced our capacity that we needed to 1/3 of what a full electrification project was. It had greatly improved economics, and then it also allowed us to set the stage for not only resiliency if the grid goes down, but an interesting thing to think of is as we move forward towards full electrification. In the summer right now, we have demand response where we're peaking in our electric and we really need to do some load shedding. We're eventually going to reach a time when we have to do that in the winter too. And so having an alternative heating source allows us to do demand response in the winter. This isn't set up at all, but I'm just thinking way down the road that it's a very reasonable future. So here is the hybrid system modified with our one line that I just wanted to put up here. In the basement, we were able to replace the absorption chillers with our condensing boilers. We installed a hybrid fan coil in each apartment. We installed the heat pumps on the roof, and we replaced the cooling tower with a adiabatic cooler. We also installed a glycol heat exchanger just because we wanted to capitalize on glycol for the outdoors because of the freezing temperatures, but we didn't want to send glycol through the building. So we have a heat exchanger just so that we're only operating with water on the inside of the building. These hybrid fan coils, I think, are the key to this whole project because it's able to work in 2 modes a little bit differently, but still capitalize on that 2-pipe hydronic network without too much change. In heating mode, it operates just as a normal fan coil would. It has a low temperature hot water coil that we're operating at around 105 degrees. And so hot water comes in, heats up the air, it returns back to the loop, very low temperature. And then in cooling mode, we have a standalone DX system that's in that fan coil with its own coil, but it's rejecting its heat instead of to an outdoor condenser. It's actually rejecting its heat back into the hydronic network. So we're keeping as much heat as possible in the system so that we don't have to fire up our heat pump and we don't have to fire up our condensing boiler unless the temperature rises or falls by a significant amount. And because each unit has one of these, it can operate in heating or cooling mode whenever it wants. Our condensing boilers were designed and chosen because it's a really great way to install a resilient gas burning solution while capitalizing on a very low temperature hot water network. It works really well with the fan coil, the hybrid fan coils that we designed, because if we operate our condensing boilers at a low enough temperature, we're condensing in our stack, but because the heat rejected in the cooling mode is coming through, if we're in our shoulder season where we may want to heat some apartments, because it's such a low temperature, we may not even have to fire up our condensing boilers to keep that system warm. And then on the roof, For the cooling tower replacement, there were several advantages for moving towards an adiabatic cooler over, a like-for-like cooling tower replacement or even a dry cooler. The main one is that cooling towers are overly regulated. Rightly so. We have to combat Legionnaire's disease, and so there's a lot of chemical testing and a lot of chemical regulation that comes with that. And so removing cooling towers is a way to not only have to avoid all of the chemical aspect of it, but you also no longer have that additional water cost as you evaporate in your cooling tower. And the reason why we chose an adiabatic cooler is because it has increased heat rejection efficiency in the system, because the mesh sides of it can actually have water sprayed onto it as the air comes down. So the air coming in is actually at a cold enough temperature where if we're rejecting heat, the heat transfer is far superior than just a dry cooler. And we don't have to deal with the chemical treatment because there's no standing water. So I want to pull up these two slides again just to put everything into perspective. And I also want to talk about how we're controlling the system. So first and foremost, we're going to focus and we're going to prioritize the hybrid fan coils. Our hybrid fan coils are going to work in heating or cooling mode, and the temperature of our system is going to fluctuate depending on, how many are in cooling or heating mode. And then we're going to prioritize, once the temperature starts to drop, we're going to fire up our heat pump, because that's where we're eventually going to capitalize on the electrified heating. And then once that's maxed out, if we're in these lower temperatures, then only then will we fire up our condensing boiler. So it was really incredible to see that this system, while it wasn't fully electrifying the building, is having a 82% reduction in their fossil fuel usage. And just to drive home how amazing this project really was, it was able to address all four of the project outcomes. There was nothing that we had to compromise on when we looked at combining systems, and we didn't really focus on hybrid, electrification. If we would have focused on full electrification, we would have had to sacrifice on something, and we weren't really required to sacrifice anything. Okay. And so just to put this all in perspective, because talking about a design is one thing and building a design is another thing. Projects do take time. We started the preliminary assessment back in 2019, and we delivered it in 2020, and we're currently in the pre-construction phase of this project, gearing up to have construction ended by 2023. And this is incredible because we're going to be able to have this building commissioned and running by the time Local Law 97's 2024 goals and limits come into play. But I implore you all to think about this, because 2024 is going to be here way before we know it. And if anything is delayed in your project schedule, it's going to just keep pushing it out, and your building's going to be at risk for these fines. So with that said, there's a couple things that just to leave you with. As we were designing this project, there were a lot of really great lessons that we learned. The first thing is that when we were looking at our full electrification project, we were really kind of stuck in a rut. And as we shifted towards combining different types of solutions and combining different types of systems, we really found that there were unlocked potential in combination. And to kind of add on to that is that perfection is really the enemy of the good, where if you're really striving for perfection, if you're striving for perfection, you're really going to beat yourself to death trying to design a project that's viable. And so being okay with not fully electrifying, but being okay with getting under the 2050 limit is amazing, because you can really work on a lot of really cool projects if you're not focused on full electrification. And then the last thing is that 2050 is 30 years from now, and I don't know any building that is not going to have to do mechanical asset renewal in those 30 years. They're going to have to do some form of change. And if you wait long enough, your building is going to have to use emergency funds to get a rental boiler, a rental cooling tower in there, and your project capital budget is going to just plummet. And so I implore all of you to think about how we can proactively approach these projects so that we can leverage the existing systems as they're still working to design projects that will help, get us to 2050 and further. Thank you guys very much. The last thing was if we have any questions. Yeah.
Sure. Isn't there already a law that in New York City they're going to ban natural gas combustion for 2030 or 2040?
So I'm not exactly aware of that. Oh yeah. To repeat the question, he was asking. New York City is. He was basically saying that New York City is planning on phasing out natural gas consumption in the future. And what I would say to that is that at the moment, I don't see how that's a feasible future, just because if you get rid of natural gas, you're creating a very vulnerable situation where you're at the whim of the electric grid, and the electric grid is very finicky as it is. And redundancy and resiliency in the electric grid implemented, I don't see how it's going to go at the moment. In the way that we approached all of these projects, we were assuming that we were still able to burn natural gas when we needed to still comply with 2050. Oh yeah, we can bring it.
And if Lucas, you can repeat the question.
I'll repeat the question.
Yeah.
Yeah, go for it.
So I guess the one answer to the gentleman's question is it's new hookups.
New hookups.
That building had existing gas connection.
Okay, that's a good.
Specific question for this kind of project.
Yeah.
Thanks to my co-op. Thanks for asking. The fan coil units that you had in the building, did you have existing electrical panels in the residential apartments sufficient to cover the hybrids, or did you have to upgrade the individual resident panels?
We had
kind of a limitation for
right. A lot of co-ops do have to have a lot of electrical upgrade in the apartments, and so his question was: did this case study require an apartment scale electrical increase capacity, correct? And so the answer was this building was actually able to cover the increased electrical capacity because the cooking of the apartment was already on electric, and so there was already an increased electrical capacity in each apartment, so there wasn't a large capacity that we needed to overcome. Yeah, I did.
No, yeah, you can.
Okay.
Just a quick question. Did you have to design or really think any, further in depth about specifically with the hybrid system, a control sequence that would optimize it, and for instance, knowing when to turn on the boilers so that they will sufficiently heat up the water in enough time to save enough energy, and have a connected type system?
Right. Okay. So his question was, if I'm correct, that how did we sequence the controls of the systems to make sure that we're capitalizing on the electric heating as opposed to just turning on our boilers and consuming that extra fuel. And the way that we designed our system is that we used a heating curve, and we had our heating curve for our air source heat pump. And basically what we did is we took that same exact curve and we shifted it 5 degrees colder for our boiler, and so that our heat pump is operating as our hot water loop got lower. If it hit our air source heat pump curve, our air source heat pump would cut on, but only until the building could no longer handle the capacity of the building along that curve, and it would continue to drop and hit the boiler curve. Then the boiler would turn on. And so we were really only prioritizing we were really only firing the boiler when we absolutely could not maintain that dead band.
The air source heat pump, the maximum can be 200 feet, like around 220 feet, so it's pretty low. So if it's more than that, then what are you going to do? let's say 22 floor or 25th floor building. So the air system can go only 200 feet high.
Right.
That's all maximum can go.
That's a very good question. The way that I would, so I really, in the context of this, I don't have a great answer for that as of now, but if you come talk to me afterwards, we can talk a little bit more about it. But there are limitations to that. And the way that I would approach it is you would design your system from the top down. If you have your air source heat pump on the roof, you can supply up to a lower floor, and then you have a separate system that would cover the lower floors, potentially either a second air source heat pump system, or you capitalize on more of a distributed air source heat pump where each unit would have its own heat pump. So it's not, it's not fully addressing how do you use a heat pump to cover the full building, but it's a way that you and leverage a different system that still is achieving the same goal.
We have a few questions from the webinar.
Cool.
As I owe them apologies, so I'm going to skip over these guys. So question came up from Natalie. Do you think adjustments will be made from Local Law 97 if electric grid isn't fully renewable?
Yes. Do you want me to repeat the question on? Okay, so the question was, do we think that Local Law 97 limits will be shifted if the grid does not achieve their goals? And I think 100% yes. The reason why 2035, 2040, and 2045 are not established yet is solely for that reason, so that as we get to that point, we can look at to see where the grid is at that time, and they'll announce the limits as we get there.
Another question. So do you plan, for instance, from Robert, do you plan on changing the chimney for the condensing boiler for this project?
So yes, we are. So are we planning on changing the chimney for the condensing boiler? And
I believe Robert has asked for the.
Yeah, we are planning on relining the existing chimney with a stainless steel stack.
And then one last question from Valerie. I guess this was during while we were talking about adiabatic cooling. Could you do the same with the electric chiller?
Can you do the same thing with electric chiller? Yes, you could. Yeah, you could do the same thing with an electric chiller, just because your condenser system is completely separate from the way that your hot water or cold water network operates. It's a separate condenser system, so it's compatible with a cold water network.
Any other questions for Lucas?
One in the back.
Thank you for your presentation. Question about ventilation. I was wondering if you could, when you were doing the original investigation, if you could speak a little bit more about the buildings existing outside air intake.
Yeah.
And a lot of people projects like these are focused on heating and cooling, not about makeup air and where's the energy coming. Either dehumidify and or heat that air.
Right. So the question is how did this project address ventilation requirements in conjunction with an air source heat pump? And what we looked at is we looked at their existing ventilation, and what we found is that each apartment had adequate ventilation coming in from the fan coil. And as we installed our new hybrid fan coil, it was still bringing in enough fresh air for each apartment. And even though we had 2 coils, we were able to remove the humidification of our cooling coil because the existing or the new hybrid fan coil had a drainage pan into it. So we were able to address the condensing issues that way. Does that answer your question? Yeah, so the fresh air makeup doesn't change with the system. Fresh air was still coming in through our fan coils originally, and we replaced the fan coils with a hybrid system, but exactly where the fan coils originally were, so the fresh air intake wasn't changing.
All right, let's give a big round of applause to Lucas. Few housekeeping items.
if you guys could fill out this presentation form. This really helps us get your feedback for all our events that we're going to be doing this year. There's a copy of it on your table too, if you can't, if it's too far or too small for you. Which leads to the next part on your table. It mentions that there is a YEA happy hour at Peter Dillon's. So Michael, raise your hand, Michael. Follow Michael, and he will bring you there. If you fill out this form, first drink is on us. So make sure you fill it. Thank you, Ben. Thank you, Ben. Apologies to the webcast people. They could not hear anything prior to the presentation. I know that was tough, but this meeting is recorded, so we will have it on the new ASHRAE New York YouTube channel. So if you guys want to visit, it should be a couple days or so. We just need to make sure you subscribe. Like and subscribe. The president said so. We'll get you another drink if you do. So let's we'll do that. But yeah, so thank you again. If you guys have any questions, I think Lucas will be at.
I'll be going to Peter Dillon. So if you have any questions, come.
Please, is there anything I missed?
Yeah, just an important note, you do need to show your back card at Peter Dillon.
Yeah, we can't help you there, so no matter how many surveys you pull out. So thank you again, guys, and hopefully to see you for the next one. So thanks.